So now that we know the general mechanism for the nucleophilic acyl substitution reaction, we want to talk about some of the reactions for this carbonyl substitution, how this generic mechanism operates in a real system. And so there are several different types of reactions that we want to go through. So let's just go through them one by one and we can see how they resemble the general mechanism. So the first reaction we want to talk about is known as the Fischer Esterification. And we referenced this last time. This is a reaction in which you take a carboxylic acid in the presence of a catalytic amount of acid and an alcohol, and in the process you can make an ester. Okay, so let's do this reaction for making ethyl acetate. So we can take acetic acid, and what we do is treat this in the presence of sulfuric acid in ethanol as solvent. So catalytic amount of sulfuric acid in ethanol as solvent. And what this will do is it will substitute the OH for the alcohol group, for the O-ethyl group. So how does this work? Well, the first thing that's going to happen is we're going to protonate the carbonyl. And we protonate the carbonyl because that's going to lead us to a more electrophilic center. Right? And so since it's more electrophilic, ethanol can come in and attack the pi star CO, move electrons up onto the alcohol as a lone pair. And so the net result that we have here is this one. Okay, and so we want to deprotonate this alcohol. It's positively charged. Deprotonate to give us a neutral species. Okay, at this point what we need to do is we need to reprotonate. Right? So the idea is we want to substitute the carboxylic acid, and so we need to protonate the alcohol here in order to make it a better leaving group. Okay, so it's now a better leaving group. What can happen now is the oxygen lone pairs can move down, form a new CO double bond. The electrons from the carbon-oxygen bond move up onto water, and now water leaves. And so what you're left with here is a protonated ethyl acetate, so it's been substituted. And then finally what we need to do is just a simple deprotonation to give us the neutral product, these nucleophilic acyl substitution product of the Fischer esterification reaction. Okay, so one modification that we can make of this reaction is that we could do this reaction intramolecularly. So the Fischer esterification is an intermolecular reaction. We have one carboxylic acid reacting with one ethanol. What if we had a carboxylic acid and an alcohol in the same molecule? This is known as a lactone formation reaction. So lactones are simply cyclic esters. And so let's say we were to take this alcohol that has a carboxylic acid on the other end, and we were to just treat it with sulfuric acid. We would generate this lactone. Right? So this lactone is just another name for a cyclic ester. Okay, and we actually number the carbons with Greek letters. So this is start at the carbonyl and you count outwards. We said that that's the alpha, this is the beta, and this is gamma. And so this is actually a gamma lactone. The gamma designation indicates that you've got a 3-carbon linker in between the carbonyl and the oxygen. But the mechanism for formation of this cyclic ester is exactly the same as a Fischer esterification reaction. So the first thing we're going to do is protonate. So you've got this protonated species, which can now undergo an intramolecular attack. And so the lone pairs on oxygen are going to attack the pi star CO, and that's going to generate a new intermediate. This new intermediate is this one, and so we need to deprotonate this charged species to give us a neutral species. And then we need to reprotonate the alcohol so that it can form a better leaving group. And then we can take the lone pairs on oxygen, move them down. Water leaves as a leaving group to give us the protonated ester. And then finally, deprotonation to give us the final product, which is your gamma lactone, your cyclic ester. All right, so Fischer esterification can occur intermolecularly, but it can also occur intramolecularly. This is taking alcohols and carboxylic acid with a catalytic amount of the strong acid to form that ester bond. Now we can also hydrolyze esters, and there are two ways that we can hydrolyze esters from the ester to the carboxylic acid. One way is under acidic conditions. Right, so let's talk about not ester formation, but ester hydrolysis. Right, so this one is going to be under acidic conditions. Okay, so we're going to take an ester this time. And we're going to react it with HCl, strong acid, and water. So water is going to be our nucleophile, and the net result that we get from this is that you're going to get the formation of a carboxylic acid plus ethanol. And so this is another sort of indication that this reaction is reversible, that these reactions are reversible, so we can go in the forward and the reverse direction. All right? So under the correct conditions, here we can get the ester to hydrolyze to the two components of the ester, the carboxylic acid and the alcohol. Okay, so how does this work? Well, first thing we're going to do is we're going to form hydronium ion, which is then going to protonate the carbonyl. That carbonyl is now ripe for nucleophilic attack, and so the electrons on oxygen are going to move up, form a lone pair on oxygen as water attacks it. And so we're going to get this new intermediate. Then, of course, we need to form a neutral species, so let's deprotonate. Now, our goal here is to sever the carbon-oxygen bond to the ethyl group, so we probably can reprotonate that ethyl ester part to generate a better leaving group. Okay, now electrons can move down from that oxygen, move up onto the ethanol as a lone pair. Ethanol leaves as a good leaving group. And then we get a protonated carboxylic acid plus ethanol. And then the carboxylic acid can become deprotonated to give you the carboxylic acid. Benzoic acid in this case. Now we can also have ester hydrolysis under basic conditions. So let's talk about that. Okay, so ester hydrolysis under basic conditions, this is known as a saponification. Okay, so let's take our same ethyl ester and let's saponify it with sodium hydroxide and water. We're going to get the carboxylic acid and the alcohol, ethanol. Okay, so in this case, we're not going to protonate the carbonyl first because we have a basic species which is much more nucleophilic. So OH minus is going to attack the carbonyl. Attacks that pi star CO and generates this species. Right, that species is going to then collapse with loss of a leaving group. Here the leaving group is less than 20, and so this works. So we get the carboxylic acid plus O ethyl minus as the leaving group. That ethoxide can deprotonate the carboxylic acid immediately. Right, so you're going to generate ethanol as one of those products plus the carboxylic acid that's been deprotonated. So we're really forming the carboxylate. Now, in order to get the carboxylic acid, what you have to do with this reaction is simply, in a workup step, add a proton. Right? So proton, in a workup step, you sort of quench this reaction with HCl. It will protonate to form your carboxylic acid. Okay, so far we've only talked about esters, how to form them and how to break them apart. Let's talk about how to make some other types of functional groups that have that can form via substitution chemistry. How about the amidation of acid chlorides? Okay, so as the name implies, we're going to start with an acid chloride, and we're going to make an amide. So in order to do that, we need to react it with an amine. So let's react this cyclohexyl system with methylamine. We're going to form an amide in this case. And so the amide we're going to form is a primary amide that looks like this. Okay, so how does this work? Well, according to that general mechanism, we're going to take the amine lone pairs. We're going to, because it's nucleophilic enough and the acid chloride is electrophilic enough, it's going to attack that pi star CO, move electrons up onto oxygen as a lone pair. Okay, so we get something that looks like this. And then we can get a proton transfer event. To give us a neutral species. Right, and then we can collapse that tetrahedral intermediate with loss of chloride is a good leaving group to give us a protonated amide and then we can deprotonate to give us the neutral amide species. Okay, we can do the same thing for the amidation of acid anhydrides. So let's try to do that in just a different type of system. Okay, so number 6 is going to be the amidation of acid anhydride. Okay, so let's take this system, this anhydride, and let's react it with diphenylamine. The product we're going to get out of this reaction is a substitution reaction in which you get 2 phenyl groups, right, attached to the carbonyl. Okay, so how does this work? Again, the anhydride is electrophilic enough to become attacked by the amine. And so we're going to get a direct attack onto that pi star CO to form a tetrahedral intermediate. Okay, so we have that intermediate. We can get a proton transfer event happening to give us a neutral species. Okay, at this point we can get collapse of that tetrahedral intermediate with loss of the leaving group. This time the leaving group is the benzoate. Right, so benzoate is our leaving group, stabilized by the resonance from the carbonyl. And we have this protonated amide species, and of course this protonated amide species can become deprotonated to give you, of course, your amide product. Okay, so we've done the amidation of acid chlorides, amidation of acid anhydrides. How about the amidation of carboxylic acids? Okay, so we want to take, let's say, a carboxylic acid in the presence of methylamine to generate this primary amide. But there's a problem, and there's a reason why I kind of put this number 7 in parentheses, because this reaction doesn't work. Now, you might recall from the reactivity series, we said that anytime you have a carboxylic acid in the presence of any base, it will become deprotonated. So the reason why you can't attack the nitrogen lone pairs onto the pi star CO, that carbonyl carbon, is because the first thing that's going to happen here is you're going to do a deprotonation. And so as soon as you do the deprotonation, you're going to generate the carboxylate, which we know is unreactive, and you're going to generate the ammonium species, which we know is dead. Okay, it doesn't have any lone pairs that it can react. So essentially, this reaction is dead. It doesn't work. Right? So the amidation of carboxylic acids is not a way of making amides. Right? It does not work. So if you cannot take an amine and a carboxylic acid and form an amide. There is a workaround, which we'll talk about in the next lecture, but you cannot take directly carboxylic acids and amines to give you amides. All right, so let's talk about not formation of amides, but hydrolysis of amides. So this reaction does work. And let's do this under acidic conditions. You might recall in the reactivity series we said that you need very, very strong forcing conditions in order to hydrolyze amides to the carboxylic acids. Well, this is the example, right? So we're going to take strong HCl in the presence of water, and what we're going to generate is the carboxylic acid, the benzoic acid, plus NH3, but I'll give it the caveat, it's really NH4 plus, right? Because as soon as you have NH3 in the presence of HCl, you're going to protonate it. But essentially what we're doing here is we're severing the carbon-nitrogen bond. All right, so this is just a nucleophilic acyl substitution mechanism, so maybe the first thing we should do under acidic conditions is protonate the carbonyl like we always do. All right, so let's protonate that carbonyl. And now this carbonyl is ripe for attack by an incoming nucleophile. Luckily, we have water around. Water attacks the carbonyl carbon. Electrons move up onto oxygen as a lone pair to generate that tetrahedral intermediate. Okay, so we can get a proton transfer event happening, or a deprotonation, to give us a neutral species. Now at this point we need to make the amine a better leaving group, and so we're going to protonate that amine because NH2 minus is not a good leaving group, but NH3 is. All right, so what we're going to do is we're going to generate that species. That charged species will then undergo collapse of the tetrahedral intermediate with loss of ammonia to generate this protonated carboxylic acid. And then that protonated carboxylic acid can be deprotonated by the amine that you that left in that reaction. Right, so this is strongly forcing conditions, hydrolysis of amides. You really need high concentrations, really strong acids, high temperatures. We also said that we could hydrolyze amides under strongly basic conditions. And I want to actually talk about this in the context of a drug. So let's talk about the last reaction here is hydrolysis of amides under basic conditions. And again, strongly forcing conditions you could use for this. But I want to talk about it in terms of the mechanism of action of penicillin. Okay, so I'm going to draw the structure of penicillin here, which is an antibiotic that some of you may have taken before. Others of you may be allergic to it. And there, of course, have been many other antibiotics developed since then. And so in some cases, this one has lost a little favor in the medical world. But at one point in World War II, this was the premier antibiotic that led to infections, or a reduction in infections, a treatment of infections, to get soldiers back on the battlefield. And the Allied forces had a procedure for doing this, and the Axis powers did not. And so what is the mechanism of this reaction? Well, penicillin is a beta-lactam antibiotic. And so where does the beta come from? Again, just like lactones, a lactam is a cyclic amide, And so we can count here alpha, beta. There are 2 carbons in between the carbonyl carbon and the nitrogen. And so we say that this is a beta-lactam, and so you can think about this as having a lot of ring strain. And so what happens with this penicillin is that you can get a serine residue, and I'm just going to label this as an OH. A serine residue becomes deprotonated in the active site of an enzyme. Okay, and that enzyme that we're talking about here is what's known as a transpeptidase. Right, so the bacteria have this enzyme called a transpeptidase, and they have a serine residue on it. And this transpeptidase is important for the formation of this cell wall. Okay, and so if you can inactivate the transpeptidase, maybe you can prevent the cell wall biosynthesis from happening, and maybe you can kill the bacterial infection, kill the bacteria. And so what happens, of course, is that serine residue in the active site gets deprotonated, probably by some histidine residue. So let's say we have this O-. Okay, well, we know that this is nucleophilic. Right, so penicillin comes along, binds to this transpeptidase, but in the active site, it will undergo nucleophilic attack by the deprotonated serine residue onto the beta-lactam. All right, so this is just simply an hydrolysis of an amide, and so we're going to get as a product of this the peptide has now been opened up. Your amide has been opened up. Okay, so first thing happens, we get a tetrahedral intermediate. There's our serine residue and the rest of the enzyme. Right, so we've got this tetrahedral intermediate, which then collapses with loss of the leaving group. Excuse me. Loss of the leaving group here will be the amine. In this case, right, we normally don't think of N minus species as being good leaving groups, but remember, we are opening up this this 4-membered ring, so there's a lot of ring strain that is allowing to compensate, allowing the system to compensate for the weak leaving group that we have. And so we get this species. Right, so this amide then takes, right, the base, right, so in this reaction up above where the transpeptidase deprotonates the serine residue to give you the O-, you also have BH plus around. So the BH plus comes back in this mechanism and becomes protonated. And so what you're left with is now a hydrolyzed penicillin. Okay, so this is now an inactivated enzyme. Your transpeptidase is completely inactivated because now it has this penicillin that is stuck to the serine residue. So it can't perform its function, and now what happens is we prevent cell wall biosynthesis from occurring. And so if you can prevent cell wall biosynthesis from occurring, you can prevent bacterial growth from happening, and the bacteria end up dying, and you recover from the infection. Now, sometimes the bacteria are smart and they develop these resistance mechanisms to this. And so penicillin has somewhat lost favor because the bacteria have evolved an enzyme known as a beta-lactamase. And the beta-lactamase will inactivate the penicillin before it reacts with the transpeptidase. And so now the transpeptidase can go on and do its job of cell wall biosynthesis, and the bacteria overcome the action of penicillin. And so we can't use penicillin anymore to treat these infections. We need to use some other type of antibiotic. And this is the hallmark of bacterial resistance or antibiotic resistance that is such a problem today in treating infection.